is hello students. As we are meeting after a long time, let me first go through what we have covered till now in this course. So what we have been discussing from our first class is this interaction between the four parameters: the material, function, shape, and process. And we have been able to establish in our earlier discussions the interaction between material and function, which actually leads us to what we refer to as material indices. Going forward, we included shape also into our discussion, and then we discussed the interaction between these three parameters, that is material, function, and shape, and it gave us what we talk about as the shape factors, the material indices that include shape, and as well as we had a discussion about what we refer to as microscopic and macroscopic shaping. In our last class, we were actually talking about designing new materials, that how do you design new materials. And I would like to move ahead out of this discussion itself on designing of new materials, which we initiated our discussion lastly in our class on what we refer to as hybrid materials and what is the need of these materials as such. Now, talking about hybrids here, so I'll now dwell upon what we are referring to as design of the hybrid materials, their reason that why we're designing them, and their definition. So what we have seen in our earlier discussions is that we have various categories of materials as metals, polymers, elastomers, glasses, and ceramics. And when we talk about hybrids here, this is what we say, that they are a combination of all these five material categories. And in our discussion on hybrids in this class, we will be referring to various types of hybrids as composites. And in today's lecture, I will dwell more upon the detailed description about composite materials as such. We will then go to sandwich structures, later on their usage, cellular structures, and segmented structures also. This takes me to our earliest discussion on the material charts here, and if you recall, this is our original modulus versus density chart, in which we have seen that according to the design requirements, you can draw the contours of slope 1, slope 2, or slope 3. In this chart, we see that we have contours of slope 1, E by rho shown here. And we already know that according to our description of material indices, the better materials are located in this zone here, and that is where we are referring to it as a vector of material development. That is why you need to develop new materials. Now, going forward from here, there's again another chart that we observe here between thermal conductivity and modulus, and we already have the basic information by now that the materials which are having a high thermal conductivity, most of them are metals, and they have very high values of Young's modulus. Obviously, there's a need to have materials in this zone, which we say is an empty zone here, means materials which are compliant and still they are good conductors of heat as such. Okay. Now, as far as materials development is concerned, as we understand that new materials there are two ways of filling the empty spaces in the material property space. You can start with the old way of doing it by developing new materials from element basis and then start filling the material property space. And there is a second option. This option, which I just said, is also referred to as what we call as the bottom-up approach. The second option, which we can say is the top-down approach, is where we will talk about as hybridization or development of composite materials, where we combine 2 or 3 materials which are already existing to create a new material. So this chart here actually tells us that how over a period of time people have developed new materials and the material property space has been filled up. So this is long ago that you had very few materials here. Moving forward here, we find that some areas are getting filled here, and what we observe that there are few natural materials which have come into picture here. Moving further ahead, we find some of the metals category has been expanded by now. Going further, and just around 100 years ago, we understand now that few more metals have come into picture. And then just around 80 years ago, around 70 years to be specific, we understand that we have a few more additions to these materials chart here. The empty space is getting filled here. So you have empty spaces which we understand are better, that your materials, if they are located in this zone, they will be better for us from certain design perspectives, and that is why mankind has been developing new materials here. This is what we understand that we stand today here, and that's what we observe in this here, that we have composites which were actually not available to us around 50 years ago. They have been created specifically to cater to demands of materials where they are required for better performance here. Similarly, when I go to the same chart between thermal conductivity and modulus, we observe that we have a blank space. We have a lot of blank space here, in which I do not have materials which are compliant, means less stiffness and high thermal conductivity. And there are possibilities which can be explored here because of hybrid materials, that you have copper. Let's say this is just an example. We have copper here which is having very high thermal conductivity but high modulus, and we have rubber here which is having low thermal conductivity but also low modulus here. So is there something we can do to create a composite so that it falls here, or a hybrid so that it falls here? And there are possibilities that you can add copper to rubber as such, and then we may land with a material in this location, or depending upon how much materials we are adding here, you may be able to create materials in this zone which were earlier unoccupied. So we will see today that how we move forward in this, and then we go to the mechanics of this designing. That's what we say as design of these composites, or design of hybrids to be specific here. Now I go back to our CES EduPack. I hope all of you have a copy of that. And if you look at one of the, again, same chart on modulus versus density, I have plotted here just to let you know there are some physical limits upon the density, to be specific, of solids. So what we observe here, that if I only plot metals here, we understand here that the lowest density metal that you observe here is lithium. Lithium having density of around 505 kilogram per meter cube, and the material which has the highest density is somewhere here is osmium, somewhere around 22,000 kilogram per meter cube. Whatever composites we need to understand this, that whatever, if I combine anywhere, all the metals are lying here. So if I combine any of them in any particular composition, we have these bounds that I cannot go below this and I cannot go above this also. Let's see what happens when I add more material categories onto this chart. And the thing is here that now what I have added to this metals envelope, we have seen that plastics also. Let's add some plastics also. So when I add that, I understand here that the limits are still the same, that I have the lithium lying at around 505 and osmium lying at around 22,000. Let's see what happens when I add ceramics into it. So adding ceramics here does not change the picture. The limits remain the same. So why I'm telling you this is just to let you know that there are some physical limits which we cannot which we cannot cross. So it may be possible to only create materials within this zone, which may be solids. Otherwise, below that, it may be possible to have materials here also, but they will not behave as solids. They may be behaving as what we refer to as foams in our discussion already. Okay. So when I refer to one of the types of hybrids, let's say composites is one of the types, we can define or we can classify composites as unidirectional composites, means the fibers are oriented in one direction only. Quasi-isotropic, where you find that they behave somewhat like isotropic, not exactly isotropic, but somewhat like isotropic materials. And you can have particulate reinforced composites here also. Then under second category of hybrid materials, we have what we refer to as cellular structures, where we understand foams, honeycombs, and triangulated lattices are there. So today, as I said, we'll only talk about the first category of hybrid materials and their design in detail on composites, and that too specifically unidirectional composites. Later on, we'll go to cellular structure material design, and maybe then we'll go to sandwich structures also. There's one more category which I have not listed here, that happens to be what we refer to as segmented structures, which may come up later for our discussion there. Okay. So let me define a hybrid. We have already defined it in our previous classes, but still just to recapitulate what we have been learning, a hybrid material we define here as a combination of two or more materials in a predetermined configuration, relative proportion, and scale. And underlined thing is that it is optimized for a specific engineering purpose. So I'll not go into the much details of this because we already have this basic definition for this. And then this is what you can write it simply as A plus B are two materials which we are combining them in a particular configuration and at a particular scale. Okay. So these are some of the possibilities which may arise. We have discussed this chart earlier in our class, and just to review that when I combine 1 and 2, the resulting one may be lying here in the material property space, that is best of both, least of both, rule of mixtures, or maybe a harmonic mean. These are the what we call as the examples of these four. That when you talk about best of both, zinc coated steel, that is galvanized steel, is one that where we say it retains the stiffness of steel and it also retains the corrosion resistance of zinc as such. Similarly, the rule of mixture scenario, which we'll talk in details about in these classes ahead, is what is useful for our discussion on unidirectional composites, unidirectional fibrous composites, which may be CFRPs, GFRPs, and the harmonic mean scenario may be available to us for particulate filled composites as such. Okay. Now, why do you need that? We already know that what is the first process in designing a hybrid or a composite. So you have to design it according to the requirements and the functions and the constraints. So if you have listed this in a design process, and if I find that there is only one material already available which is able to suit all these requirements here, we have a very simple solution and we end up with that particular material only. But more challenging cases arises when we say that there is no single specific material which is there through which can fulfill these requirements, and that is why you need to then see that maybe function 1 is better performed by one material, function 2 is better performed by second material. The example which I always give is of a GFRP composite, where the glass fibers are maybe very good in function 1 like stiffness, they are having very high stiffness, and the matrix may be a polymer matrix which is very good in function 2, that is having a very good toughness here. So when I put them together, you may combine them and then a hybrid solution may be achieved. Similar thing can be said about various configurations here, about sandwiches, lattice, and segment structures here. Okay, now discussing about unidirectional composites, we see here that this is just an graphical representation of what unidirectional composite looks like. It's a line diagram in which we understand that this is what we have, the fibers. The fibers are oriented along one direction, along this direction. This direction will be referring to as L direction, so the longitudinal direction of the fibers. And in this context, I define what we refer to as the material axis system. So we define L as the longitudinal axis, this axis, which is the axis aligned with the length of the fibers. Sorry. Yes. So if we have the longitudinal direction, the length, which is the direction along which the fibers are oriented. The other two directions are T and T prime, and we say that T happens to be the transverse direction, the x is normal to L, and T prime happens to be the direction which is normal to both L and T. So I'll be referring to, so obviously when we look at this description of a unidirectional composite, unidirectional means fibers are only in one direction. And obviously according to the properties, the stiffness here will be more along one direction and less along the T direction. So we may be then having different formulations developed in our next slides about modulus in the L direction and then modulus in the T direction, that is the transfer direction. Obviously I'm referring to this unidirectional composites here as an anisotropic material which does not have same properties along all the directions.